Welcome back. This is our week 8 of Graduate Statistics, University of Cincinnati. We're just reviewing the independent activity assignment to get you warmed up for the content of this class. So we said we're finalizing here. We said that the p-value is virtually zero, so the probability of observing this mean, if assuming that the male population has a mean of 35 and that percentage of body fat is normally distributed, then it's not very likely that we would see such a large deviation from the mean. So we reject the null hypothesis, and that's consistent with the confidence interval. See that 35 is not in there, so the decision is the probability of data, the probability of observing that this X bar is very, very low, and then we reject the null hypothesis in favor of the alternative. Now, I will always ask you from now on to interpret the result in the context of the question that we asked. I want you to be able to look at the results of your statistical analysis and speak about them without using statistical jargon, basically providing a data-based answer to the question. So here is the interpretation. Data provides evidence that males have less body fat than females. And this is your parameters in the statistical sense. You have the Z, because it's a Z sampling distribution with a center of 35 and a spread of 0.12, like this is the standard deviation of the sampling distribution. And the observed is negative 96.61, and the p-value is 0.00. So the difference observed is quite large. Considering a 90% confidence interval, the average percentage body fat of males is between 22.98 and 23.38. So even the higher the upper boundary, reflecting the most conservative estimate, is quite far from the average body fat percentage in the female population, which is 35, right? And actually, instead of using this, the best would be to say the probability of observing the average that we observed in our sample, if the null hypothesis were true, if the percentage body fat of males were 35, is less than 0.0001. It's virtually zero, right? So this result suggests that the difference in body weight is substantial and could indeed be related to the greater risk of atherosclerosis and its devastating consequences. Just remember, however, that the fact that I'm saying that the difference in body weight is substantial, it has nothing to do with the p-value. It has to do with these values here. So it's more than 10% difference, even if I consider the upper end of the estimate, right? So we have a very precise estimation here. Take a look, it's a very small interval, somewhere between 23 virtually and 23.4, right? And that is about 10 less, more than 10 less than the female population. So the magnitude is substantial. So something may be statistically significant, but the difference might not be that large, right? 10% of difference in body fat percentage is a lot of difference, right? It could be impactful clinically. All right, so now we're ready to move on. We're going to assess mean differences when population variance is unknown. And remember, in the case of the z-test, we can estimate the population variance using the sample standard deviation because we have a large enough sample size to make the estimate of the variance in the population reasonably accurate. When we have smaller sample sizes, that estimate is not accurate. So we need some corrections in order to apply hypothesis tests. And that's what t-tests are for. So let's look at this in more detail. What purpose does a large sample serve? As long as observations are independent and the population distribution is not extremely skewed, A large sample would ensure that the sampling distribution is nearly normal and the estimate of standard error is reliable. Remember, the estimate of standard error is obtained by the standard deviation of the sample divided by the square root of n. But the standard error is really equal the variance of the population divided by square root of n. So we want this to be a good estimate of the variance in the population. Right? So we want this to be, it has to be a good estimate. Now the t-distribution, why is it useful? It is useful for describing the sampling distribution of means. When the population standard deviation is unknown, my sample does not provide me with a good enough estimate of the variance of the population, and hence sampling error cannot be estimated reliably. So when we cannot apply the central limit theorem to construct the sampling distribution. So we need something else to put in place. When the variance is unknown, which is almost always, because almost always we don't have a super large distribution that's not very skewed, so we can use the t-distribution to address the uncertainty of the standard error estimate. The t-distribution is bell-shaped, but it has thicker tails than the normal distribution. So if the dotted line is presenting you with the normal distribution, the t, note that the tails are a bit thicker. So there is, for the same two standard deviations, say, above the mean, there is a greater probability of finding stuff for the t than for the z distribution. So observations are more likely to fall beyond the two standard deviations for the t distribution than for the z distribution. Extra thick tails are helpful for mitigating the effect of a less reliable estimate for the standard error of the sampling distribution. So it will take larger deviations from the mean for me to reject the null hypothesis when I'm not quite certain of the variation. So I become more conservative. Okay, before I can dismiss the null hypothesis, I need bigger changes that are typically beyond two standard deviations. Now, like the z-distribution, the t-distribution, the standard one, is always centered at 0. It has one parameter, degrees of freedom, that determines the thickness of the tail. And what is the degree of freedom? How is it calculated? So let me track back for a second. The normal distribution has two parameters. For you to draw the normal distribution, you need a mean and you need a spread. The t-distribution, you also need the degree of freedom. It's one extra parameter, okay? And that parameter will tell us what the thickness of the tails is. And the degree of freedom is related to the sample size. All right, so it's the sample size minus 1, typically, okay? We'll see how that varies a little bit, but it's very highly related to the size of the sample that you have. And if you have then a larger sample size, what happens is that the thickness of the tail begins to shrink and shrink and shrink and shrink. And if you have enough degrees of freedom, then your t-distribution will look a lot like the z-distribution, which makes sense because we're using the t-distribution when we have a smaller sample size. If we have a big sample size, we might as well use the z because the t and the z will be basically the same, will provide us with the same results. All right? So it approaches the normal distribution as the degrees of freedom increase. For inference on a mean, so you want an inference on a mean. Is this mean bigger than that value of the population? For inference on a mean where variance is unknown, again, which is almost always, we rarely have a very large sample size. Then compute t, okay? The t, look at this formula. It looks a lot like the z formula, right? You have the observed average minus the null average. Imagine if we were doing the study on the percentage of body fat, but instead of having that very large 6,000 people sample, we had only 10, right? So we would have the observed mean, and we would have the null hypothesis, which was, again, 35. And we would compute the standard error in the typical way, all right? But we know that this error, this value, will be not as precise, so we'll compensate by having thicker tails and requiring greater deviations before we can reject the null. So then, once we get the t, which is how much deviation from the mean, from the null, do my average has, then I can get the probability of the observed t under the null hypothesis, which is again a p-value. We can use 1 or 2 tail area of the t-distribution as opposed to z depending on HA, right? So if I have a directional alternative hypothesis that the observed is smaller than or greater than the null, then I put my 5% all to one side, either the higher side or the lower side, either the upper side of the curve or the lower side of the curve. If I have a non-directional hypothesis, I just expect a difference, and it could go either way, then I distribute my rejection area in two sides. I have 2.5 here and 2.5 here. Okay, so my rejection area is smaller on each side because I don't know to which side things are going to go. And we use R to get the probability. So a bit of mechanics with illustration to visualize these rejection areas. Suppose you have a two-sided hypothesis test and your test statistic is 2. Under which of these scenarios would you be able to reject the null hypothesis at the 5% significance level? Let's look at the z-distribution, which you learned last time first. Imagine you got a test statistic, z statistic, that's 2. If you're running a two-sided test, you want the probability of getting a value of either -2 and lower, or 2 and higher. So more extreme than absolute value of z, right? The probability of getting an absolute z greater than 2, which equals to the probability of getting -2 and higher, and -2 and lower, and 2 and higher together. That's why when we used p-norm, we would put 2 and then just a positive value and then say that we want the upper tail, but then we would multiply by 2 because the probability of getting 2 or higher is identical to the probability of getting -2 or lower, okay? And that probability is 0.045. So it's less than 0.05, which makes us reject the null hypothesis. Now, what happens with the t-distribution when I get a value of 2? Again, if the t-value is 2, the tails are thicker, so that probability will be higher of seeing 2 or higher, -2 or lower. And to do that, instead of running a p-norm, I'm going to run a pt function. And again, the value of 2 right here. I want a 9 degrees of freedom. Imagine you have a sample size of 10, so the degree of freedom will be 9. And we'll put that to false and multiply by 2 again because it's a two-sided test. Note that if you get a z statistic equal to 2, you're going to reject the null. If you get only 2 standard deviations above the mean on a t-distribution, you will not reject the null hypothesis if it's a two-sided test, because the p-value would be greater than 0.05. So what I want you to think here, don't worry too much about this because we have a super efficient function for running t-tests. But what I want you to think about is the idea of having a thicker tails, that you will need a larger deviation from the null for you to reject the null. Here is that example. If you have just a 2 deviation, it's a z distribution, you would reject. And if it's a t-distribution, you would not. We'll come back and discuss the t-distribution a little bit more with examples to help ground everything. All right, see you then.